First, let's look at bond polarity. Bond polarity begins with the difference in electronegativity between two bonded atoms. We write this as delta En. Electronegativity is an atom's ability to attract shared electrons. Delta En is the absolute difference between the two electronegativity values. A larger difference produces a more uneven pull. In H2, both atoms have an electronegativity of about 2.20. Delta En is 0, so the electrons are shared equally and there is no bond dipole. In HCl, hydrogen has an electronegativity of about 2.20, while chlorine is about 3.16. Delta En is about 0.96, so chlorine attracts the shared electrons more strongly. Electron density shifts toward chlorine. Chlorine becomes partially negative, shown by delta minus, and hydrogen becomes partially positive, shown by delta plus. This separation of partial charge creates a bond dipole. The dipole arrow points toward the more electronegative atom, chlorine. In general, a larger delta En gives a stronger bond dipole. Now, let's move to molecular polarity. First, use delta En to identify the bond dipoles. Then use the three-dimensional molecular shape to determine their directions. Finally, add the dipoles as vectors. The same polar bonds can produce different molecular polarities when their three-dimensional arrangements are different. That is why molecular shape matters. Each bond dipole has both a direction and a strength. The direction comes from the molecular geometry, while the strength is related to the electronegativity difference in that bond. If the vector sum is 0, the bond dipoles cancel completely and the molecule is nonpolar. If the vector sum is not 0, a net dipole remains and the molecule is polar. Consider carbon dioxide. Oxygen is more electronegative than carbon, so each carbon to oxygen bond has a bond dipole pointing toward oxygen. Both carbon to oxygen bonds have the same electronegativity difference, so their bond dipoles have equal strength. Because the molecule is linear, they point in opposite directions. The oxygen, carbon, and oxygen atoms lie on one straight line. The bond angle is 180 degrees. Equal dipoles pointing in exactly opposite directions cancel completely. The net dipole is 0, so carbon dioxide is nonpolar. Now compare carbon dioxide with water. Oxygen is more electronegative than hydrogen, so both oxygen to hydrogen bond dipoles point toward oxygen. The oxygen atom has two bonding pairs and two lone pairs. Repulsion between these electron groups gives water a bent molecular shape. Because water is bent, its two equal bond dipoles do not point in opposite directions. Therefore, they cannot cancel. The two bond dipoles combine to produce a net dipole toward the oxygen side. The oxygen side is partially negative, and the hydrogen side is partially positive. Water is therefore polar. Next, consider boron trifluoride. Fluorine is much more electronegative than boron, so all three boron to fluorine bonds are strongly polar. Boron trifluoride is trigonal-planar. The three fluorine atoms are evenly spaced around boron, and every fluorine-boron-fluorine bond angle is 120 degrees. The three bond dipoles have equal strength and are arranged symmetrically. Their vector sum is 0, so boron trifluoride is nonpolar. Ammonia also contains three polar bonds. Nitrogen is more electronegative than hydrogen, so all three nitrogen to hydrogen bond dipoles point toward nitrogen. Nitrogen also has one lone pair. This lone pair changes the molecular shape from flat trigonal planar to trigonal pyramidal. In this pyramidal arrangement, the three bond dipoles do not cancel. A net dipole remains toward nitrogen, so ammonia is polar. Now look at methane. 4 hydrogen atoms surround one carbon atom in a symmetrical tetrahedral arrangement. Carbon and hydrogen have a small electronegativity difference of about 0.35. Carbon to hydrogen bonds are therefore usually treated as nearly nonpolar. The tetrahedral arrangement is also perfectly symmetrical. Any small bond dipoles cancel, so methane is nonpolar. Carbon tetrachloride also has a tetrahedral shape, but each carbon to chlorine bond is polar because chlorine is more electronegative than carbon. All 4 carbon to chlorine bond dipoles have equal strength, and the 4 chlorine atoms are arranged symmetrically. The dipoles cancel completely, making carbon tetrachloride nonpolar. Now replace one chlorine atom in carbon tetrachloride with hydrogen. The new molecule is chloroform HCCl3. Chloroform is still tetrahedral, but the atoms around carbon are no longer identical. Its charge distribution is no longer symmetrical. The carbon to chlorine electronegativity difference is larger than the carbon to hydrogen difference. The bond dipoles therefore have different strengths and cannot cancel completely. Chloroform is polar. Dichloromethane has 2 chlorine atoms and 2 hydrogen atoms attached to the central carbon. The molecule is tetrahedral, but the 2 types of outer atoms make the charge distribution uneven. The stronger carbon-to-chlorine bond dipoles are not cancelled by the much weaker carbon-to-hydrogen bond dipoles. A net dipole remains, so dichloromethane is polar.